All right, we're continuing with the lectures on chapter 9, and this is going to be a review of what we've already covered, but um, it's a good review because it goes through step by step and has pictures, which I think are much more helpful than the notes have been because a lot of the notes have just been notes with no pictures, to go along with them. So let me go ahead and get my pen ready. All right, so the first step in the generation and propagation of an action potential is that an end plate potential is generated at the neuromuscular junction. That's the very first step. An end plate potential is generated at the neuromuscular junction. So this end plate potential causes a wave of depolarization that spreads to the adjacent sarcolemma. So all of the events that we've just been talking about, the action potential reaches the axon terminal of our neuron, of our axon, and calcium ions then enter in because calcium gates are opened up, voltage gated calcium channels are opened up. Calcium ions enter the axon terminal and activate the synaptic vesicles, which contain acetylcholine. The synaptic vesicles fuse with the plasma membrane of the axon terminal and then release acetylcholine into the synaptic cleft by exocytosis. The acetylcholine then binds to these little purple receptors and acetylcholine receptors, and those are chemically gated channels that allow sodium to enter. So if you have started out with a negative voltage, so if it has been negative all through here, on the inside of the sarcolemma. That's basically the sarcolemma, remember, is the plasma membrane of the muscle. So the muscle fiber. So what we're looking at here is a negative voltage or a negative potential is what we have for the resting potential, the resting membrane potential. So what's going to happen when sodium enters is that you're going to have excess positive ions. So when you put positive ions in an area that's negatively charged, it's going to become more positively charged, and that's depolarization. And once the depolarization happens at one point on the sarcolemma, it will then spread to the rest of the sarcolemma, causing it to also depolarize. So you have the positive charge, positive, 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 negative going to positive, negative going to positive, all the way down the sarcolemma. And eventually the sarcolemma is going to form into a T-tubule, and that depolarization is going to propagate down the T-tubules as well. So the notes on depolarization, let's see if there's anything we need to highlight. If the end plate potential causes enough change in membrane voltage to reach a critical level called threshold. And what that means is if the resting membrane potential is negative 70 millivolts, threshold is usually somewhere around negative 55. So if there is enough sodium ions coming into the cell that this potential reaches at least negative 55 millivolts, we call that threshold. If that is reached, then you're going to have more sodium channels opening, more voltage-gated sodium channels, because the voltage change is what opens those channels. So then you will have a large influx of sodium. That means that sodium is going to come in very, very fast, and that is what's going to cause an action potential to spread across the sarcolemma from one voltage gated sodium channel to the next. So that's what causes the spread of the action potential. And that is the meaning of propagate. When we say that it propagates, I think I misspelled that. No, I didn't. Okay, so propagate and spread are pretty much the same thing. It's just propagate just means that the depolarization moves from one point to one voltage gated sodium channel to the next one beside of it. Okay, so it spreads. In step number 2, depolarization, generating and propagating an action potential. It just says depolarization opens voltage gated sodium channels. Action potential is generated and it spreads to adjacent areas of the sarcolemma. Opens up more sodium channels. So this is just showing like propagation of the action potential down the sarcolemma or plasma membrane of the muscle fiber. Then you're going to have repolarization. So at some point, the sodium voltage gated channels are going to close, and voltage gated potassium channels are going to open. They're going to open in response to a positive voltage due to the sodium ions coming in, and that when that voltage reaches high enough, that positive voltage is going to trigger those I keep doing that. I did this on the last video. I'm very sorry. K is potassium. This is a potassium ion. I'm sorry, I have said calcium a few times. Okay, so the potassium is going to diffuse out of the cell because there's a very high concentration of potassium inside the cell. So when you open up voltage gated potassium channels, potassium's going to move out. So if you think about this, if sodium ions coming into the cell if sodium ions coming into the cell causes the membrane potential to become less negative and more positive, then the opposite's going to be true when potassium ions move out. So the membrane potential is now going to become more negative, okay? And that's what repolarization means. The efflux of potassium ions is going to bring the cell back to its resting membrane potential or voltage. So it's going to go from -70 to -55, and that's going to be threshold. And once threshold is reached, it's going to, a lot of sodium is going to come in, and that's going to cause the potential to become even more positive. I think up to positive 30. And that will trigger potassium channels to open and sodium channels to close. And now that we're at positive 30 millivolts, now that we have positive ions leaving the cell, it's going to become less positive. So it's going to go back eventually to that -70 millivolts, which is our resting membrane potential. Now, there is a period called the refractory period where you cannot stimulate the muscle fiber for a specific amount of time until repolarization is complete. That's a short period of time where the muscle fiber cannot be stimulated. It's called the refractory period. And the resting state, the resting membrane potential is restored and maintained by the sodium-potassium pump. And that sodium-potassium pump, just to remind you, pumps out, let's write this, sodium potassium pump. What that does is continually pumps out 3 sodium ions out of the sarcolemma for every 2 potassium ions that it pumps in. And that helps to maintain the negative 70 millivolts called which we call resting membrane potential. And that is step 3, is showing you here that the repolarization happens when the sodium channels close. There's a little gate that closes over that channel so no more sodium can come in. And now the potassium, which is high inside the cell due to the sodium potassium pump, is going to diffuse out of the cell when those potassium channels open. So if positive charges are moving out, then the membrane potential is becoming more negative again, okay? When you're losing positive charges, then you're becoming more negative. This is a graph that shows you basically what happens in a muscle cell. Muscle cell resting membrane potential is a little different from a nerve cell resting membrane potential. So instead of negative 70, it's negative 90. So what's going to happen is sodium channels are going to open, and that potential, because sodium is positive and you've got sodium positive charges going into the cell, you're going to make it less negative. So it's going to travel up toward the 0. And then once threshold is reached, then, and threshold can be various numbers. I gave you negative 55, so we can just say if threshold is negative 55, sodium channels are going to open and sodium is going to then rush into the cell. And that's going to very quickly raise the membrane potential to a positive value, positive 30. The positive 30 voltage triggers the sodium channels to close and the potassium channels to open. And now that we have no positive ions going out, but we do have positive ions coming back in, I said that opposite. I'm so sorry. I don't want to re-record it though, so just understand. I caught my mistake. I'm really sorry. Now that we have no more sodium ions coming in and all we have is positive potassium ions going out, that's going to cause if we're losing positive charge, then we're going to become more and more negative and eventually reach that negative 90 millivolts, that resting membrane potential. Okay, now something happens called excitation contraction coupling. Excitation contraction coupling. And these are the events that transmit the action potential along the sarcolemma being coupled to the sliding of the myofilaments. So coupling the excitation caused by the action potential with the contraction, with the actual contraction of the muscle. So what happens is the action potential is propagated along the sarcolemma, and the sarcolemma eventually folds down and into these T-tubules, which go deep into the muscle fiber and transmit that action potential deep into the muscle fiber so that it can cause the release of calcium ions from the sarcoplasmic reticulum. And those calcium ions will trigger the muscle contraction. Okay, so what's happening, what we're talking about is happening on the next page, I think. Yeah. Okay, so here's your T-tubule carrying the action potential deep into the muscle fiber and the calcium release from the sarcoplasmic reticulum. It's going to attach to the troponin.